So yesterday, guys, we talked about a couple different types of reactions in depth. We talked about synthesis, we talked about decomposition, we talked about precipitation. Today, we're going to start with a little talk about acid-base neutralization. So, to date, we have been talking about ionic compounds as dissolving in water. We learned yesterday that not all ionic compounds dissolve in water. We've talked about covalent molecules all staying bonded together when they dissolve in water. They can dissolve, but they stay bonded together. Well, now we're coming up with a new idea, which is acid-base neutralization. So in acid-base reactions, a proton is exchanged between two molecules. The proton donor is called an acid, and the proton acceptor is called a base. Now, acids, whoops, I always do that. Acids are molecules that can ionize by releasing an H+. Right? So, this is our first time observing molecules. These are covalently bonded atoms becoming ions in water. All right? So, an example of this is if you put hydrochloric acid in water. You're like, oh, two nonmetals, so this is going to stay as a molecule. Well, acids are a special case where acids actually dissociate into ions, and you get H+ and Cl-. Okay, so there are a couple different things we need to know about acids. Acid. So for now, we're going to there are like all these different acid-base definitions. There's Arrhenius, Bronsted-Lowry, Lewis. For now, what we're going to worry about with acids is that acid donates an H+. It gives it away. We're going to, chapters 17, 18, and 19 are all on acids and bases. For now, all we need to know, acids donate an H. And generally, have a chemical formula starting with H. This is general, and this is for now. We're gonna delve in deeper later on. But for now, things start with an H. You can assume they're going to be an acid, except for one thing. H2O, but actually water acts as both an acid and a base. So a strong acid completely ionizes in water. So, which is to say, all H pluses removed or donated. So it breaks up completely into its ions. Weak acid only partially dissociates. So it stays as the molecule, but also dissociates. And so we have strong acids, weak acids, and let's use our SAT skills. Polyprotic acid. What do you think? Oh, yeah. Yeah. But also dissociates a little. Sorry. Thank you. So, how? So, let me add a slide in, and I'll show you in a second. Do you have a question, Eric? Yeah. So no, the question was like H2CO3 is a weak acid, so does that partially dissociate into H+ and HCO3-? Yes, but that's not why it's a weak acid. That's not exactly the thing. I'm going to show you in a second. Okay, polyprotic acid. Let's use our SAT skills. Poly means multiple. Protic, what do you think that means? Protons. And why can we call H plus a proton? That's all it is. A hydrogen H plus ion is just a proton, right? It's one proton, 0 neutrons, and it lost its electron. So it's just a proton, so we call a polyprotic acid has more than one ionizable H. So there's more than one H that it can donate per molecule. So like Eric mentioned, H2CO3 has 2 H's it can donate. H2SO4 being the strongest polyprotic acid that we're going to talk about. All right, so I'm going to add in a slide if you guys need me to wait for another few seconds. No. So this is a sidebar. All right. So, Emma, give me a color. Blue. Okay. How can an acid be weak? What does it mean? Blue. Oh, thanks. All right. HA. You can do it underneath. Yeah, right under. The question is there anywhere you can do this? Just underneath polyprotic acid. HA is, we'll say it's a weak acid. So if I put HA into water, here's what it'll look like. Something along these lines. Okay, so most of it stays covalently bonded together, but a few of the H's can break off from the A minus. Yeah. Mm-hmm. Acids can absolutely dissolve in other solvents. In fact, when we delve into it later on, we're going to talk about ionization constant and things like that, and we'll talk about it a little bit more. Okay, so in the realms, I keep saying I hate memorization, but this unit, there's like a couple of things you need to memorize. One is the 7 strong acids. Does anybody know like the dwarves? I don't know. Happy, sleepy, dopey. I don't know. Grumpy. I like how Eugene came up with grumpy. Sneezy, bashful. All right, so, oh yeah, Doc. Okay, so 7 strong acids. These are ones that completely dissociate. So, let's see how many we know. HCl. Oh, hold on. Bucky's. Nope. Yep. Nope. Not HF. Everybody thinks HF is a strong acid because of Breaking Bad. HF is reactive, but that doesn't make it a strong acid. So strong acid means it completely dissociates. HF sticks together because it has to do with the orbital overlap being so similar in size. But we'll talk about it. So I just gave you a hint. HF is not a strong acid, but HCl is because of orbital over. HI. Good job. So there's another one in that. HBr. And then there are the 2 that even I never really remember. Nope. These are the ones that chloric and perchloric acid. Really, guys, these are the 5 that are most important. And really, if you want to get super most important, those are the ones that are like the super most important. Okay. So these are the 7 you have to remember. These are the ones that all donate a proton. So the one that's a little tricky is this one. I don't know how much. So this like Eric was saying, is completely dissociated, we say. And then this one partially dissociates. Don't worry overly about this step yet. This is more chapter 17, 18. Which feels so far off, but we're already at 10. Already at 10. Yeah. I know, right? Okay. Oh, darn it. Son of a gun. I hate it when that happens. Gotta fix this now or I never will. All right. So now we get to bases. All right. Okay. A base accepts a proton. Error. So we're going to generally see these in two types for now. One is ionic bases. So ionic compounds ending in what? What should we look for in an ionic compound for it to be a base? OH, ending in OH. Now be careful. Molecules ending in OH are what? Not bases. Do we remember what OH is in a molecule? Hydroxyl group, alcohol. So those aren't bases. We're looking for ionic compounds ending in OH. Or we are looking for many molecules with nitrogen can act as bases. Yep. Amino acids, like a lot of that stuff has the COOH is the acid, the N group is the base. Yeah. It does. So the question was, if you add OH minus to H plus, don't you just get water? Yes, is the answer. So when we start classifying them, that's what we're going to see. Many molecules with N. So for example, ammonia. Ammonia acts as a base. This is the smell that you might be used to from hospitals and stuff like that, that ammonia smell, because it's used as a cleaner, right? So it reacts with an acid to make ammonium. So see how the NH3 accepted a proton and made ammonium. So that's how it acts as a base. So the N can accept protons and become NH4 plus. Yep. So why does it accept the H? It has that lone pair, and it's very electronegative. So it's pulling on those electrons tightly, and the H is close, so you have this area of negativity that proton can be attracted to. I don't know. I'll ask the organic chemistry guy. What other atoms can act as bases? I mean, nitrogen's the big one. Right. So for neutral things, just the N, but then you can have charged particles that can act as bases. Yeah. All right. Okay. So now let's do some reactions. All right. So Eli, you just said don't H plus and OH minus, just make water. So what are what's one of my products going to be? Water. And then what's left? I want you guys to try to draw a particulate representation of this. So do the 2 beakers beforehand and then the 1 beaker after. So take your time, draw what you think this is going to look like from a particulate point of view. Going to the cards. Who cares? So I hear sorry, I'm going to put this out there even for the people listening at home. Don't be afraid to get called on. Who cares? We're all in this together. What's the worst that could be happen? Oh my God, you're wrong. People are going to judge you forever. No. No. Jesus, that's ridiculous. I know, that's the thing. Why would you care? Right? Okay. Connor. Help me out, buddy. What am I gonna draw? All right, shh, be respectful, please. Mm-hmm. Yeah. All right. Okay. So let's do symbols. Give me some symbols. So we're gonna do a circle for H. And that's okay. All right. So what about Cl? Just give me another. All right. Now, this HCl. Shh. No. What's it? HCl is a strong acid. So what do we say about strong acids? Yeah, they completely dissociate. So what I would do is I would draw like an O. Maybe. Whoops. A square. I can draw squares. All right. Okay. So now, give me 2 more symbols. All right. There you go. All right. So the triangle is going to be Na plus. The Superman is going to be OH minus. Now, going back, I'm going to take Connor off the hot seat. Going back to yesterday, what did we learn about all compounds that have Na plus? David, all ionic compounds with sodium. If I put them in water, what's going to happen? They can dissolve in water, right? So this is going to be all right. Now, Eugene, how should I draw the product? Yep. Na and Cl are still separate, so I'm going to have 2 triangles and 2 squares. Water is in the water. Okay. All right. So, but here's the thing. You would need to draw them bonded together. So these are bonded together. The shapes are bonded together. So the H plus and the OH minus actually form a covalent bond with one another. So they are actually physically bonded together. The NaCl, because it's aqueous, is still dissociated. But the H2O becomes liquid. So it's almost, when we talked about the partner swap yesterday and a precipitate, water almost acts like the precipitate here, right? Except instead of being a solid, it becomes a liquid and you can't see that it was made. So the question was, unless the ratios were perfect, there'd be other leftover stuff. If you were doing a balanced equation, you would balance it until the ratios were good. But if you mixed them and the ratios were off, you'd have leftover stuff. It wouldn't be all neutralized. If you put in too much acid, it would still be acidic. If you put in too much base, it would still be basic. Right. Okay. Let's do some. So the product of an acid-base reaction tends to be water and a salt. Not always NaCl, although it happens to be in this case. Water and a salt. / a salt's just an ionic compound. Yeah, we consider ionic compounds to be salts. Yeah. Hmm? The question was, are they all tasty? No, some of them are very quite deadly. HCl would, well, but HCl is not an ionic compound. It is a covalent molecule that dissociates. So, like, magnesium chloride, I can't imagine tastes great. Although, you never know. I mean, I'm sure some people know, but. All right. Oh, damn it, I did it again. The sad thing is I should know because I have it in front of me. But I just get so excited. Yeah. All right. Okay. So, all right, guys, here are 3 examples. Do the examples, please. Okay. Yeah. Yeah. What? Eugenio? I did this. I don't know. Eugenio.
Eugenio.
Okay. So, guys, let's do. Check your Check your answers. All right. So a comment came from over here. Like, can you just start with water? Yes. Just start by writing down water, because you know that's going to be formed. All right. So here I have 2 H pluses, 2 OH minuses. So that's going to make 2 waters plus Ca C2H3O2 2 aqueous. And then here I have 6 H pluses and 6 OH minuses. So that's 6 waters plus Ba3PO4 2. Now, I have a question. Is barium phosphate soluble or insoluble from our solubility rules? Insoluble. So what will this actually make? Solid. It's still a salt, but it's a precipitate. So you still need to look at your solubility. This is rare-ish. Why are all the questions about what is or isn't on a test? All right. So this is what we're going to talk. We're done talking about acid-base reactions. You'll see a bunch of them on problem set 10. And then our last little bit of our last type of reaction, oxidation reduction. So, guys, listen up. Crayon. All right. All right. I don't want to like yell. Not that I would ever yell, but I don't want to be like loud into the mic. Be quiet. Like, all right. So, in oxidation, or what we call redox reactions, electrons are transferred from one atom, molecule, or ion to another. So this, you are looking at the transfer of electrons. In redox reactions, looking for transfer of electrons. To keep track of who's gaining and who's losing, we assign each an oxidation state or oxidation number. Now, if this is about the movement of electrons, what might be one possible application for redox reactions? We want moving electrons. Battery and electricity. So this is very important for what we're going to call electrochemistry, which is going to be the last unit we study this year. This is chapter 21, is electrochemistry. So redox reactions, really the first batteries that were ever made were redox reactions. In fact, your batteries that you use today in your cell phones are all redox reactions that involve the transfer of electrons from something that wants it to something that wants it less. I mean, the other way around. Wants it less to what wants it more. Yeah. So the question is about the different reactions. There are multiple different redox reactions that are used, but in battery storage, they're all some form of redox reaction. Not like the electricity we generate here for our lights and stuff that comes from our power plant. That's different. But for in batteries, yeah, it's a redox reaction. So the question is, how does a rechargeable battery work? When we get to electrochemistry, we'll see we can make the battery, if we allow the reaction to happen favorably, it'll go one way. But if we put electrons into it, we can force it to go back the other way. So you're recharging it. It's basically what direction the reaction's going to go in. Okay. So general rules for assigning oxidation states. And we need the oxidation states to see what gets oxidized and what gets reduced. All right, there are a few variations, but they'll all give you the same result. General rules. For a monatomic ion, the charge equals the oxidation state. So what would be an example of a monatomic ion? Na. All right. So Na plus, oxidation state is +1. Right? For a molecule or a polyatomic ion, the sum of the oxidation states of all the atoms must equal the total charge. So throw out a polyatomic ion. Ion. SO4. So SO4, all of them have to equal -2. When you add them all up, they have to equal -2. Right. So to assign, but we're going to have to assign oxidate. The question is, isn't SO4 just charged? Yes. So SO4, really SO4 2- is what I should say, is equal to -2. So the sum of all these is going to be -2. So the oxidation state in total will be -2. And I'll show you how to do that in a minute. Yeah. For each covalent bond in a Lewis structure, we assign +1 to the less electronegative atom and -1 to the more electronegative atom. This one is not going to come up very frequently. These will come up a lot. Frequent. 3 comes up less. And the formal charge is added to the result of step 3. So this also comes up very infrequently. Really, when we're doing redox reactions, 1 and 2 are important. And then the following page. Following rules are also listed. The oxidation state of a pure element is 0. So if I just had Na, if I had neutral sodium, I would assign that 0. So any neutral atom is 0. F is always -1. And now it's like prioritizing, right? Pure element is 0. F is always -1. O is always -2, except when bonded to F or when bonded to itself. So I'd say the question was, do you have to memorize it? I would say yes, yes, yes. It's probably all going to be yes. Yes. Yeah, sure. These are all things you need to know. Yeah. So the question is, how is F not a pure element? So if I had like, HF, right, in a compound, H is +1, F is -1. So that's what as people are writing all over Alex's notebook after he asked the question. All right. So this is how it would not be pure if it's bonded to something else. So oxygen is always -2 except when it's bonded to F. So like OF2, oxygen doesn't have a -2 oxidation state. And H2O2, so really it's O2, the peroxide ion. But these are very rare. Remember, O really doesn't like to be bonded to itself. So that's not going to happen very frequently. Peroxide is really reactive. Yeah, Eric. F can form ionic and covalent bonds. And so you're going to use 5. 5 is going to be really helpful to you. So the sum of all of the oxidation states in a molecule of polyatomic ion or ionic compound must add up to the total charge. It's similar to 2 on the previous page. So let's practice. We'll do 1 together, and then I have 5 for you guys to practice with. All right. So potassium permanganate, KMnO4. What type of bonding is present here? Sonia. Ionic. So how would this split apart? All right. So we know the oxidation state of potassium is +1 because that's the charge of the ion. Now we use our other rules. The sum of this has to be -1 for the whole thing. Do we have a rule about one of those other 2 atoms, Eugene? Right, so we have Mn plus 4 times -2 equals the sum, which is -1. So Mn minus 8 equals -1. Mn equals +7. So we got a little math. Starting with chapter 11, this course gets a lot more math heavy. So if you're like me, that's awesome. If you're more conceptual, we'll work on the math. So the question was, how did I get -1 as the sum? Because the charge of this ion is -1. Good question. All right, so guys, on the next page, come up with your oxidation states for all of the different elements in those compounds. No, so the question was the oxidation state be 8 altogether, each atom. So this would be +1, +7, and -2, but it's -2 times 4, so -8 and +8 has to equal 0. Yeah, Owen. All right, guys, how we doing? All right, so I'm going to walk through this. I'll walk through a couple, and then I'll put up the answers. So H, we'll do it in order. O is always what? -2, thank you. H is +1. So we have 4 times -2 is -8. So we'll just do it. So S plus 4 times -2 plus 2 times +1 equals 0. S then has to equal +6. So see how I summed them all up? And the sum had to be 0 because this is a neutral molecule. So then O is -2. Br has to equal +1. H equals +1. N equals -3. K equals +1. N equals -3. O equals +3. Na equals +1. How about C and N in this case? Okay, why do you think? Okay, so the problem is you have to look at the Lewis structure and use that rule that I said is very rare. All right, so for each bond in your Lewis structure, the more electronegative atom gets what? -1. So N is -3. C, more electronegative, is +3, but it has the negative formal charge. So C equals +2. That one was hard. +2. Because it's +3 from the 3 bonds, and it has a -1 formal charge, so +2, +3 minus. +3 minus 1 is 2. Math. All right. So this is one of those cases where you actually had to do the Lewis structure. All right. Now, why do we care? Why are we doing this other than the curriculum says that we have to do it? All right, guys, we got 5 minutes. Let's see if we can get through. Leo the Lion says grrr. Did you guys do this in honors chem? No? All right, good. I'm glad we're getting into stuff that's new for everybody. All right, in a redox reaction, we already said electrons are transferred, right? Oh, I didn't tell you, real quick, I showed my spouse the test that I gave you guys, and she's like, this might as well just be another language. So I'm looking up here, I'm like, could anybody out who didn't know, like, redox, reaction, E minus, it's like we do have our own language, right? Reaction, electrons, what's that? Estabop. All right, okay. So we say, Leo the Lion says grr. Grr. That's my lion voice. Grr. Now, what does this mean? The substance that loses electrons is the one that's oxidized. If it gains electrons, it's reduced. If there is one, there must be the other. So in any redox reaction, you have at least one substance that is losing electrons. We say that that substance is oxidized. If you have a substance that's oxidized, those electrons had to go to something, so that means you're gaining electrons and it's reduced. So in any redox reaction, you have both of these things happening. So it's like in biology with NADP and NADP, NAD and NADH. Is it right? NAD plus. Right. Yeah, there's a lot of oxidation reduction that goes on in biology in the body, transferring oxygens around, right? And electrons and, right. Okay, so let's figure out, how do we do this? We look, we say what is being oxidized and what is being reduced. That's why we need to know oxidation state. So start by writing down the oxidation state for each of the compounds, or each of the substances in this chemical equation. Start by writing down the oxidation state. It's better not to be a jet. It's better to be. Okay. All right. So let's go. Iron. Solid iron. What is the oxidation state? 0. It is in its pure elemental form. It is 0. NO3 stays the same on both sides, so we're just going to say this whole thing is minus. So what does Ag have to be? +1. NO3 is -1. Ag is +1. On this side, what is silver? 0, because it's elemental, it's by itself. And Fe +3. So in this case, I literally write down this. So which substance lost electrons? Guys, what lost electrons? Fe lost electrons. It went from 0 to +3, so it had to lose some of its electrons to do that. Ag gained electrons to go from +1 to 0. So iron was oxidized. It was Leo'd. Ag, silver, was GERD, so it was reduced. Okay, we'll finish up on Friday. Have a